All right, this is my project on the math of machine learning. I'll start off by talking about what machine learning is. The goal of machine learning is to make predictions based on trends of previous data. It directly applies the math that we've learned this year, both linear algebra and multivariable calculus. Machine learning can mainly be divided into two categories, classification and regression. So classification is the prediction of a qualitative variable. For example, image recognition, finding out what the object is in an image would be a classification task. And a regression is the prediction of a quantitative variable. And below is an example of a regression task. So this left table is a small data set that gives the house prices for these particular house sizes and number of bedrooms. The goal of a regression is to find a mathematical model that will allow us to predict future house prices based on this house size and number of bedrooms. If we were to make a reasonable estimate here, we could guess that this one's maybe around 60,000 and this one's, 600,000 and this one would be probably over 1 million. So the goal of machine learning is to make a model that can accurately predict these house prices. So I just want to review some linear algebra real quickly. So the dot product of two vectors of the same size is the sum of the product of their corresponding elements. And for matrix multiplication, each element in a resultant matrix is the dot product of the corresponding row and column of the previous two matrices. So the reason why I want to show you guys this is so you can see the similarity between the dot product and the matrix product. I think that it's relatively less intuitive to understand matrix multiplication, or at least see the usefulness of it. So whenever you see a dot product, start suspecting that we can also use a matrix multiplication. And of course, I'm talking about this because a matrix multiplication is particularly useful for machine learning, which will become more obvious on the next slide. So I'll quickly describe the data that we're working with. We have a matrix X that contains all of our data on these houses. This data set has the data for M houses or samples, and each sample has N predictive values or features. To make a prediction, we can assign a coefficient to each of these features to determine how important or correlated that feature is in predicting the house price. And we can make a column vector of these coefficients and call it theta. For these approximations, it's useful to have a column of ones, which can act as like a constant value, kind of like a y-intercept. Since this is our known data set, there will also be a column vector of values that will contain the true house price for each of these M samples. And this vector y will be useful for calculating the error of our predictions. It would be pretty helpful to remember the dimensions of each of these. So to go over it one more time, we have a matrix X of data with dimensions m by n plus 1, and a vector theta of coefficients of size n plus 1, and a ground truth vector of size m. In order to make a prediction y hat, each coefficient would naturally need to be multiplied by its respective feature in x. And to take all the variables into account for a prediction, let's just add all of them up. This, of course, assumes that these variables are independent. Linear regression is a relatively simple model, and other models handle potential relationships across variables better. This particular type of approximation indeed looks a lot like a dot product. Corresponding elements for each x and theta are being multiplied together and then added. And now we can start thinking about matrix multiplication. We're basically doing this for every sample x, so if we just stack them on top of each other, this becomes matrix multiplication. Therefore, y hat is equal to x times theta, and y hat is a column vector with length m, which is the number of samples. So we have a prediction for each sample. If we don't actually think that the relationship is linear across all these features or dimensions of the data, we can simply add in terms of higher power as shown in this bottom right corner. If you'll remember, any function can be closely approximated using a polynomial of high degree. And if we really want to, we can actually just put any function of x here and slap on a corresponding theta. We now have a way to predict the house prices, but we don't actually have the coefficients for theta yet. If we want to mathematically define exactly what theta would be most preferable for us, it would be the coefficients that result in a prediction that deviates the least from the known values for the house prices. Hence, we need to define a function that gives the error of the prediction as a function of theta, and find theta such that this error/cost function is minimized. Hence, we define j, the cost function. It is the squared average deviation between the predicted value and the known ground truth value in our vector y. You may notice that this is actually half of the average, or half the squared average. The reason why we do that is so that it cancels when we take the derivative to find the minimum of the function. The reason I've been talking about matrix multiplication so much is because a lot of effort has been put into making matrix multiplication very fast computationally, and it would be a waste not to use these methods, especially when matrix multiplication is so clearly applicable. So just for fun, I put down this vectorized version of the cost function. You might notice this transpose here. Computationally speaking, column vectors are exactly the same as n×1 matrices. Since x times theta minus y is a column vector, we need to transpose it into a row vector to get a dot product. Now that we have a cost function, we need to find a way to minimize it. And this involves a little bit of multivariable calculus, since we have multiple independent variables or features. This is an iterative process. This colon equals here is an assignment operator. Essentially, we're assigning the value on the right side of the colon equals to the symbol on the left side of the colon equals. And since this is iterative, the symbol on the left side will be continually updated until convergence is reached. We want to find the derivative of the cost function and move in the negative direction of that derivative, which would be towards the minimum. Specifically, we want to do this for every coefficient of theta. Therefore, we need to take the partial derivative of theta of j with respect to each theta and move in the direction that decreases j as a function of that particular member of theta. This figure is a contour graph of a mock cost function j. The redder lines are the higher values of j and the bluer lines are the lower values. This particular j only takes into account two thetas, theta 1 and theta 2. So we take the negative partial derivative of j with respect to theta 1. We assign the new theta 1 to become this value, so we would move in this direction for theta 1. We do the same thing for theta 2, taking the negative derivative and moving in that direction, leading us to this point on the graph. And we continue to do this until the derivative of j reaches 0, meaning that we have hit a minimum. Using a computational method like this tends to be better than solving algebraically like we did in multi. The main advantage of gradient descent is that it's faster. For example, there is an equation called the normal equation that will output the optimal values of theta no matter what, but its computational complexity is higher, meaning that it takes longer to compute than the gradient descent. Now, let's find the derivative of j with respect to theta. It's easiest to do this if we consider this problem for a single theta j at the moment. The process should be the same for all thetas, as you saw on the previous contour graph. As you hopefully remember, the sum of the derivatives is the same as the derivative of sums, and you can just pull out the constant, so we can skip straight to this step. This power rule should be relatively self-explanatory, though I personally thought the chain rule here is a little bit less intuitive, because we're taking the derivative of a single element of x theta minus y with respect to theta j, not with respect to the entire theta vector. So to make this a little bit more clear, I split up x theta minus y into a summation form. As you can see, this is just a dot product because we're only concerned about one I at a time, so we're only multiplying by one row of x for each theta. Since we're taking the partial derivative with respect to theta j, we only care about this term, and of course the derivative of this term is xij. Therefore, the derivative with respect to theta j of j is 1 over m, the sum of x theta minus y xij. However, this equation is not vectorized. There's a summation and there's no like matrix multiplication involved. So in order to vectorize this, let's just investigate this sum for now. So this sum looks a lot like a dot product. It's a summation of the products of corresponding elements of x theta minus y and the jth column of x. Here's the summation written as the dot product. This notation here just means the jth column of x. And since these are just vectors, we can swap the order and the dot product will still be the same. So if we simply layer each row of x into a matrix, then this becomes matrix multiplication, and we get a result of the column vector theta. We can then repeat this operation until convergence. So that's basically all you need to know for linear regression for machine learning. We know what the data looks like, we know what the cost function is, and we know how to optimize thetas to minimize this cost function. And that's about it for linear regression. I'll go over neural networks now, which is a different type of machine learning algorithm. Neural networks are a very powerful general type of algorithm, and they're often used for classification tasks. If you look at the diagram to the right, which you've no doubt seen before when people talk about machine learning, these last four nodes each represents a class. The network will output values closer to 1 for the node if it predicts that the input is associated with that node's corresponding class. So let's say we have a neural network trained for image classification. This is the input layer, and that would be something like pixel values. And this is the output layer, and it would be the object that the neural network thinks the picture is of. So let's say this represents a person, like a picture of a person, for a car, for a bird, or for a tree. So if the neural network thinks that the pixels consist of a picture of a tree, this node value would become 1 and all the other ones would become 0. There's quite a bit of notation to go over, so I'll explain that. Let Aij represent the activation of the ith unit in the jth layer. The activation is essentially the input for a node. So A11, that's the activation for this node. And let L be the number of layers, so each of these is one layer, and S sub j is the number of nodes in that layer. So for this layer, there'd be 5 nodes. The weights of a neural network are essentially the same as the coefficients for linear regression. This time we need a matrix data between each layer instead of just a vector, as we need a weight for each connection. So here there are 3 nodes, and each of them are connected to 5 other nodes. So here there would be 3 times 5 connections, and that can be represented as a 5 by 3 matrix. Here you might notice there's a +1 that represents the bias unit of the next layer. Basically, it's the same thing as the constant column for linear regression. So when you're actually implementing the model, there would be another layer here, another node here, and that would be the bias unit. It's connected to all the output nodes, but not to any of the inputs. So that's just adding a constant to all of these. Finally, this sigma is the sigmoid function. It's the family of functions that we've used in the past for logistic growth. These node outputs have a range of all real numbers, which is not entirely practical, so we want to cap it off at some point. So with the sigmoid function, we'll force the range to become between -1 and 1. Now we can define the activation for a node. It is the sigmoid of the dot product of the weights and activations of the previous layer. We can vectorize this definition, and if you want to think about this graphically, the activation of one node is the product of each connection. Well, it's probably better to use this. So it's the product of each connection to each of the previous activation values, and they're all put through a sigmoid. Now we need to optimize our weights, and we do this through a method called backpropagation. Uh, the general idea is that we calculate the errors back from the last layer all the way to the input so that we can calculate the derivative of the cost at each layer. This method's not necessarily unintuitive, but it is relatively messy, so I'm gonna just go over the high-level things. Our high-level goal is to find the partial derivatives of J with respect to every element in the matrices of theta for every layer. This way we can do gradient descents for all the thetas to find the optimums. We'll start off with a simple cost function, which is just the squared error. AUL is the prediction at the last layer, so it's the output, and this is the ground truth value y. Since AUL is dependent on theta, we're going to have to do a chain rule, and it's always less complicated to do calculus with scalars, so I've broken down AUL into a summation form as well. And that's about it. We can calculate the derivative of J with respect to AUL, and AUL with respect to theta UV, as I've written here. Though as you notice, this is only for a single layer, L-1, the second to last layer. If we want to go deeper, we have to do the chain rule again with the activation of the previous layer. And this time is different as well because we need to sum over the nodes of the last layer. This one activation, L-1, is going to affect the cost function in multiple different ways. Specifically, SL number of ways, the number of nodes in the last layer. It can this activation function can affect the cost function through this weight as well as through this weight. So you need to sum across all of them. And you can do this chain rule all the way back to the input layer, and that is your full backpropagation method. Now that we have every single partial derivative, we can do gradient descent for each weight. And that's about it. That is linear regression and neural networks in a nutshell.